Right, morning guys, I think. So, my name's Alex Chapman, and I'm here to talk to you this morning about hacking an internet-enabled Lagomorph. Or more precisely, hacking an internet-enabled Lagomorph. So who am I? I'm Alex Chapman, I said that bit. Work for Context Information Security, vulnerability researcher over there, and newfound interest in Internet of Things devices. Starting this talk, I kind of feel like I need to put a bit of a disclaimer on it and have to explain my situation. So those of you who were in my colleague Mike Jordan's talk this morning, he would have spoken to you a little bit about an event we held internally, and I'll just recap that. So when this whole Internet of Things kind of thing kicked off with big interest in this new buzzword of basically embedded devices, we thought, okay, we'll give it a shot. We'll get a load of devices together, have an evening, all the guys in the office, we've got beer, we've got pizza, we've got things to hack. The stage was set, absolutely perfect. So we've got things like IP cameras, light bulbs, office peripherals, a few kids' toys and things. So as we go on, so we kind of start this project off quite well, go off in groups, pairs, and solo, and we fight against these devices. The evening wears on, and a lot of these devices start to fall to the guys, or start to show interesting avenues of attack that can be pursued later on. Late into the night, we're obviously all a little bit drunk by this point. We declare victory. The majority of the devices that we've looked at, we have been able to compromise. And you'll see that from some of our previous work, and as I say, my colleagues thought that was just before this one. And we kind of got together and we presented the results. So we had these IP cameras. Okay, admittedly, this was a bit of a cheat. There were some known issues in these devices, but at the end of the evening, they were thoroughly hacked. So we got one of these internet-enabled light bulbs you may have seen. And by the end of the evening, okay, not entirely hacked, but we knew precisely how we were going to do it and that it was feasible. So I chalked that one up as a win. Office peripherals fell immediately, and the printer showed some really promising attack surfaces. And the thing I'm about to talk to you today, we didn't manage to hack. So I hope a number of you will understand my situation here. How can I let this one device go? This is the one that got away, and it's a kid's toy. This talk isn't any cutting-edge research or anything like that. This is more a group therapy session, I think, for myself. Being able to kind of talk this through and follow through my madness to the end point where we did actually manage to compromise this. So please bear with me. Feel free to leave at any point when I start ranting or throw things or tell me to get off stage. So introducing Karotz. I guess this is the big reveal. And here it is. So I broke the power supply, so I've got a bit of a dodgy stand going on there. This is Karotz, the smart companion, a stylish communicative rabbit connected to the internet, if you read the marketing material. I mean, really, that's what it is. I think that was $100 worth of electronic rabbit there, so money well spent. But what Karotz really is, so it's an ARM-based embedded device. It's got a Samsung ARM9 processor in there, 2 GB flash memory, 512 SD RAM, Wi-Fi, obviously, and it's a Linux-based embedded device. Despite the connotations there, I'm fairly sure this rabbit isn't going to start the machine uprising and the apocalypse, but bear with me on that. Yeah, bizarrely, I'm not the first person to try and compromise this rabbit. I was astonished when I found that out. So Daniel Crowley of Trustworthy Spider Labs has done some prior work on this, and I am thoroughly indebted to him. So if anyone knows him, or if he's here, please let me know and I'll buy him a beer. So he's found 2 previous issues for which he did submit CVEs for. I'm not quite that organized, but so there's Python module hijacking issue, and that is actually quite key. I do build on that, so I do genuinely thank him for that. And also for noticing that it doesn't use SSL. Important issue, but there we are. So that's some prior art, should we say. I'm building upon Dan's research from that. So let's just start with any new device, kind of looking at the attack surface. What have we got? So the main issue that Dan came up with was a physical attack. So you need physical access to the device, to the USB stack, and to be able to turn the rabbit on and off. That's great, but I kind of prefer to do these things remotely. So I took out USB. I took out you get these little RFID tags as well. I took those out. I wasn't that interested in being that close to this thing. It scares me. So the network-based attack surfaces. So if you get more than one of these, you can get them to talk to each other. It's fantastic. So there's network protocols between the two devices, so they are actually listening on a couple of local ports. And then the guy does kind of talk out to various internet-enabled servers, so most importantly, the Karotz server in the back end. There is a text-to-speech engine. I was dying to demonstrate that today, but I haven't been able to get internet set up, and some of my demos are a bit dodgy, so I don't think I'll be able to show you that one. And like any kind of new startup, you can write apps for this thing. So you can write an app that goes away and reads you the headlines from BBC News. That's a brilliant one. And all of these apps talk to individual servers out in the internet that other people own. The scary part of that is a lot of these apps have access to the webcam and text-to-speech engines and all the rest of it, and they're running on somebody's home server. But we'll ignore that for this point. So I was mainly interested in the kind of Karotz server communication at the top, and then the device-to-device communication. So in terms of kind of network stack, the Karotz is actually listening on two TCP ports, so 6600, which is running Music Player Daemon, and 9123, which is actually running the Karotz controller service, it's called. And a little bit more on those in a little bit. Right, so getting started, again, I'm starting at the real start here. This is probably teaching you all to suck eggs, but first thing I wanted to do was get hold of the firmware. A number of ways of doing this. Can try and pull it off the chip on the device. Easiest way, just go download it from the Karotz website. So did that and found that they quite cleverly GPG encrypted the majority of the hard drive image. So kind of okay, a bit of a stumbling block. Try and get onto the device, try and do some clever stuff with it. While I'm there, I'll update it. And it turns out it doesn't actually use this GPG encrypted version of it. It just goes down and downloads an unencrypted version of the file system. So perfect there. Get hold of the firmware and can start to tinker around with it and look what's going on. So this is where we come up against a kind of a typical choice when we're doing this sort of thing. Are we going to try and do on-target vulnerability research or off-target vulnerability research? So a bit of a catch-22 for on-target VR. We kind of need a way to instrument and to debug the device before we can compromise it. But being able to get that, we need to be able to compromise it. You see where I'm going with that. So I thought, right, OK, Dan Cowley's bug aside, I will start with off-target debugging. So I will pull off the files I'm interested from the firmware and run it on an external device. So what ARM devices that I have lying around in the office that were easily extendable and accessible, usable? Turns out Raspberry Pi, brilliant bit of kit, absolutely love it. It is an ARM 11-based processor rather than ARM 9, but it actually has binary compatibility with ARM 9 compiled binaries. So literally lift and shift from the Karotz firmware onto the Raspberry Pi, run it in a true-rooted environment, and we were good to go. So first target, I thought I'd start with MPD. So Music Player Daemon. The configuration file, again, lift and shift from the device, which very kindly showed us the default password, which was Karotz. So you can already tell they've thought about security when they're doing these things. So I've got full access to the Music Player Daemon. So where do we start? So we start with simple fuzzing instrumentation against this Music Player Daemon. So it was version 0.15.0 on the device, so that's the one I'm using on my Raspberry Pi. And I'm fuzzing it, and it falls within seconds, and I mean seconds. Simple HTTP fuzzing, and the thing falls over, and repeatedly falls over. So looking at this is, I guess, a summary of the issue that I found there. I did apply for a CVE for this one, because it was a library that some people do actually use. And it turns out the bug was actually in this library, libNNS. So this is for downloading playlists using the MMS and MMSH protocols. And this issue actually allowed full corruption of the MPD process heap. So a little bit of an overview of that issue. This getAnswer function is responsible for processing HTTP response headers. So we'll kind of run through each of the headers in turn, copy them into another buffer, and then do something else with them if it's one it knows about and has to deal with. And the important line there is highlighted in red. It reads a byte from the input stream, stores it in a buffer until we get to a new line. Really, really basic issue we're seeing here. Reads a byte. Is it a new line? No. Increase the length. Sorry, increase the counter. Read another byte. Is it a new line? No. Increase the counter. You can see we can just flood straight off the end of the buffer there. No length checking, and into the process heap. So really good, really kind of very typical issue. The buffer was stored in Heap Memory. It was a pure C application using it, and there was very little interesting data on the heap. In fact, I think this buffer was the only thing on the heap. So we don't have any of the kind of standard ways of exploiting this. Very few options to manipulate the heap layout. The only thing we can do is download these MMS files. And as far as I'm aware, the heap allocator it was using wasn't vulnerable. So yeah, okay, an issue, but of limited exploitability in this instance, I was fairly sure. While I'm here, a brief note on disclosure and remediation. So I did report this issue to the developer of libmms, and fantastic effort on his part, turned around a fix and released a new version within 18 hours of the initial report. That's stellar. I've not seen that before. So a quick shout out to the libmms guys. So great, first vulnerability in a shared library. Not a lot I can do with it at this point. I'm sure I could have invested hours and hours and hours looking at heap allocators. I didn't really feel like it at this point, so on I go. That was where I very quickly came into the hit a limitation of off-target VR and off-target debugging. So that was pretty much the entire functionality of MPD exhausted. It's a very small daemon, doesn't do very much. So wanted to look at the next service. So same again, lift and shift from the Karotz firmware onto my Raspberry Pi and hit a snag. This thing's looking to talk to various hardware peripherals, for example, the speaker, the ears. It's an important one, the ears, other things like that. And if it can't access them, it just craps out. It just dies there and then. So I've got a choice of trying to patch up these binaries so they work without the peripherals, or give in and build on some previous research to get an on-target debugging environment. So yeah, really thanks to Dan Crowley, I did use his bug to get an on-target debugging environment. I pretty much said all of that, didn't I? Okay, so one key point of this, so Dan's bug did allow us to get code execution, and I'll cover how that happened in a second. What I wanted to do was put my own firmware on there. So you look at the firmware update scripts, how they work, and get rid of most of the kind of sideline stuff. The really two key functions were these flash erase all and nanowrite built-in commands. So all I need to do is call flash erase all, wipe the flash, and then rewrite it with my own firmware. Fantastic. So Dan's bug. So this is the Python module hijacking bug, so CV 2013-4867. For those who don't know, Python module hijacking is very similar to DLL planting or path poisoning on Nix systems. So when importing a module from a Python script, if it's not a standard module, it'll look through various an array of paths to try and find the module. And the first path it checks is the current directory. So this is not great security from the Python guys, but and it has found use in actually quite a few exploits, I believe, recently. And this is one Dan pointed out last year. So in order to run code on this device, all you need to do, stick it on a USB stick with with a name of simpleJSON.py. So the update script tries to import simple.json. You provide your own implementation of simple.json, which just does what you want, and then exit out. So the script I use here, very simple. I added some external debugging, so as soon as it loads, it runs an MP3, erases the flash, puts my modified firmware on the device, and then plays the MP3 again so I know it's done. And my firmware update, really quite simple. Add a new user to etc password and enable telnet. That's all I need. From there, I can do everything else I want. Using a little trick here that a lot of Linux sysadmins would probably have me beheaded for, but the CTX user I added with UID GID 0, so adding another root user rather than changing the password of the root user. Just leaves things a little bit neater in terms of modifying the file system, but yeah, not really great practice. So success. I can now log in to my Karotz over telnet. They had this very interesting MOTD script that runs when you log in. So it looks like at one point they were actually expecting people to log in, or they did this for their own purposes when they were doing the development. So great, I'm on the device, I can run my own code, I can start to debug and run services on the device with the correct hardware. Absolutely perfect. Except the device doesn't ship with any debugging tools. Why would you? It's a kid's toy. Why would you have GDB server on there? So we've got to cross-compile all of these. Cross-compilation, absolute pain in the ass. This is actually the first time I came across Buildroot. A fantastic project if you're ever working with any ARM kit. Buildroot is fantastic. Lets you build a cross-compilation toolchain on x86 or whatever your normal OS is, in order to be able to compile all the useful tools. And it will, just with a couple of clicks of a make script, compile GDB server, strace, pretty much all the debugging tools you need. Set up the right architecture, build all of that, and I think an hour and 20 minutes later after compilation, I had my debugging toolchain there. So absolutely perfect. I'm on the device, I've got my debugging tools, now what do I want to do? So this is where I want to start looking at this Karotz controller service. I said at the start, this is the service that's responsible for communicating with the back-end Karotz servers and the peer-to-peer rabbit communication protocol. Not entirely sure what they call it, but that's what I've called it. And again, as noted in previous research, all of this happens without any encryption. So that's another barrier down. First thing I want to do, and I always like to do when I'm doing VR on these sorts of devices, try and remove any third-party servers. Nothing worse than having an application or a device crash, and then it send a crash log out to the developers straight away before you've had a chance to look at it and actually do anything with it. So first thing I wanted to do was remove the dependency on the Karotz server. Starting to look into the Wireshark captures of the communication, and a frustrating couple of hours of trying to identify what the protocol was, and I find out they're actually using Google protocol buffers as the underlying protocol communication protocol. So for those who don't know, Google protocol buffers is Google's language-neutral, platform-neutral, extensible mechanism for serializing structured data. It's a very simple way of parsing data on a low-level protocol. The specification is very good and gives you all the information you need. But as a quick example, so it's a simple tag length-based protocol. You say what the data packet is and how long it is, and then it's interpreted from there. To build one of these, you provide it with a specification, which is the bottom left, and the data you want to be sent, which on the right there. It's then combined into an intermediate representation, and then this is the resulting data you'd actually see on the wire. And then, obviously, the reverse process can happen the other end. It looks at the specification, pulls the data back, and decodes it all. We're at a slight disadvantage here because we don't actually have the specification. Oh, no, sorry, skipping ahead of myself. To do this, I did use James's Canopy tool. So those of you who went to James's workshop yesterday be very familiar with all of this. And it did help out a lot, so thanks, James. One of the huge issues reversing this process is we don't have all the information that we require. And protocol buffers is actually reverse non-deterministic. So given an amount of data on the wire, we can estimate what it would have looked like based on the specification, but there are some edge cases. So consider the following piece of data that we identify on the wire. So it looks like that. We decode it into its tagged format, which can actually be decoded in two separate, both valid ways. And then if we take that one step further, we could end up with either of these two original packets. So we could have an unknown message with a nested message inside, or we could have an unknown message with just a string inside. Obviously, looking at it and analyzing it in person, we can see it's probably meant to be the top one rather than the bottom one, but it's actually quite difficult to script that up. So there are some edge cases when reversing Google protocol buffers, but we can make a pretty good estimate of what it should have looked like. So then, worked out what protocol it's using, what it's doing, set about trying to remove the third-party server. And as I say, there's a number of reasons for doing that. And actually, one of the main ones was their servers are really unreliable. So just as I'm getting started with all of this, their servers go down. I can't talk to the device because it won't open up ports if it can't talk to the server. A really big hassle. So let's try and get rid of that. So analysis of the protocol shows it gives simple hello message, registers the applications that it's got on there, tries to configure its time zone, and then it's just a consistent ping pong. And quite usefully for us, it actually ignores most of the responses, which is brilliant. So really simple to set up an offline server. And hopefully, it's the start of my demos and the start of where things are going to go wrong. So let's see if we can show that. Right. No, that's not the right one. Right, so top window here. With any luck, if I turn this guy on, you can see his ears moving in a minute. It's brilliant. When he loads up, yep, it's starting. It'll poll out for all the various services it requires, but this is the only important one. So there we go. The Karotz backend server. Just realized this takes a little while, so probably should have started this before. I'll come back to that when he's actually doing something interesting. This is what got me interested in this project from the very start. Right, so here we go. So we can see he's sent his hello message out, registering his applications, and then just starts the ping pong process. So without replicating that server, I wouldn't be able to demonstrate any of these or any of this in this room because I haven't set up internet access. But with that, I can do this entirely offline and wherever I am. You get weird looks if you start trying to hack this thing on a train, by the way. I've done it. It's people stop and stare and then call the guard. Great, so I've got rid of the requirement of the server. That you're not seeing that anymore, are you? Sorry, PowerPoint doesn't like me switching between screens. Start somewhere around here. Yeah, great. So got that to a point where I can do offline VR on it and crack on. So starting to look at the peer-to-peer protocols and just throwing messages at it, really. There's some really nice debugging that gets put out to the console, which tells you the contents of the decoded message. Run through all of that, start to build up a view of what the protocol should look like and what it requires. Once you've got a basic overview of the protocol, sending it long strings of A's is always a good thing to do. So this is the first thing. So this is a login packet. So it tries to authenticate to the device, because the device does require authentication before you can do anything. So again, they have thought about security. If it works on a session-based authentication that I'll cover shortly. So if a connecting client sends it a session with lots of A's, again, we get a nice heap corruption. It's brilliant. This is better than the first heap corruption we had. But I'm tired of heap corruptions. I'm not willing to spend the time to try and massage the heap, get it in the right way, then produce the shellcode, then run the heap. It gets complicated, and I was fairly sure it was unnecessary. I'd found this one within seconds. I figured there would be more bugs and probably more easily exploitable bugs. So the one key thing it did let me do was crash the Karotz server, which actually we'll see in the next couple of bugs did come in real handy. So then keep going, sending other types of messages, all the rest of it. Various things are happening. And then I figure, right, okay, I don't really understand what's going on, so I'll actually start reversing and debugging the application that I'm attacking. I'm a bit lazy. I'll do that after I do the initial fuzzing. So come across the authentication routines, because that's where you've got to start. Try and pull that apart. Right, I'll just cover off quite how Karotz does its authentication. It's really quite complicated, so hold on to your seats. Karotz actually has a mobile app, which I forgot to mention earlier, so you can actually kind of play music from it, view the webcam, get it to speak stuff from your mobile. In order for the mobile device to authenticate to the Karotz, it first talks to the Karotz backend server, sends username and password. The backend server then sends a session ID, so this interactive ID, down to the device and back down to the phone, and then the phone uses that as a shared secret with the Karotz device. It's fantastic. So the authentication function in the Karotz is very simple. It literally just compares the received interactive ID with the one it's got stored. If they match, you're authenticated. If they don't, you're not. However, as soon as you start the device, so on a fresh boot, the interactive ID is set to the empty string. Anyone see a problem with this? The authentication function checks if the string you send it is equal to the one it's got stored. It's currently storing the empty string. Does the empty string equal the empty string? Yes, fortunately it does. So as soon as this device starts up, or as soon as the controller starts up, the session ID is set to the empty string. Can we restart the service so that at any point we know the session ID is going to be the empty string? Yes, we can crash the service. We've already proved that. So at this point, I can now authenticate to the device using the empty string, as long as it's only just booted. If it's not, crash it. The service boots up, and I can authenticate. Great. So it's time for, I mean, this is the main demo of the talk. If this doesn't impress you, please just leave. So this gives me access to a lot of functionality on the device, and unauthenticated. Oh, wait. If I could type right. Oh. Is that right? You see that? Unauthenticated ear wiggling, everyone. At that point, I thought my job was done. I was just going to go home, but somebody said that wasn't enough. How is that not enough? One I was playing with earlier that I was trying to get working. I'm not sure if it will work. Let's see. Nope, thought it was too much of an ask. You can get it to play music, and as I say, text-to-speech engine, that's always quite a fun one. You just sit it on people's desk and have it cursing at them the entire day. But great, so I can actually now start to do things with this device that, again, I probably could have done from my mobile, but I can do it unauthenticated. And you can make it move its ears, which, believe it or not, never gets old. I'm going to have this problem again, aren't I? Great, so why was that actually important in the long run? Why was that really good for me? So I've now got a much bigger attack surface. So originally I had this authentication packet, and that was it. That was my limitation. But now I've got everything beyond that. So let's say this thing does actually have a stupidly vast amount of functionality. But key ones are playing audio files. Okay, how well are its audio libraries implemented? You've got the kind of standard reading from the microphone, taking pictures from the camera, and you can see that's why there's tape actually over the microphone and the camera, because it was scaring me. Ears, obviously you've got the ears. You've got a lot more attack surface to play on. So this is when I started to actually look, what was the functionality of these? What was doing this? What was responsible for the playing audio? What was responsible for capturing the video? All the rest of it. Turns out, looking through the firmware image, they're using music player daemon. So no, sorry, the other one, mPlayer. And mPlayer is a kind of quite standard music and video player for Linux, and they're actually handing off to that to do any of the playing of music. Happens through a call to system. I thought, brilliant, there's no way they're going to have done their arguments properly. I can definitely break out of that and run whatever I want. And I think, in fact, I'm certain it's only by accident that it's not vulnerable, which was a huge shame. But turns out they are using a slightly older version of mPlayer, which has known vulnerabilities. Fantastic. It's not finding my own ODE in it, but if I can get code execution, I am more than happy. I can go home and I can leave this carrot alone. This carrot's alone. Carrot. So vulnerability number 4, mPlayer remote file overwrite. So this is, I say, known vulnerability, advisory released September last year. Very little public information available and no public exploits, unfortunately. The advisories are very short and don't provide very much information. So mPlayer contains a flaw that may allow a malicious remote server to overwrite a file on the victim system. Okay, that sounds pretty good to me, but doesn't tell me how to do it. And similar other advisories. It wasn't until about 3 days ago I looked a little bit further and found one with a bit more information, but still not quite enough to do a final exploit. So what do? mPlayer is open source, so we use the source. Grab version 1.1, grab version 1.1.1, which has the fix, diff them, and we should, in theory, find the problem. So that's what we'll do here. Turns out the major differences were in this ASX parser function. Version 1.1 there, version 1.1.1 there. They had a big message saying support for specifying parameters in playlists has been disabled, and they comment out the function. So what this function actually does, and this is brilliant from the guys who did this, it allows a playlist to specify the command line functions that should have been passed to mPlayer. So you download a playlist, it specifies parameters that change how mPlayer runs, basically. It's brilliant functionality. So to exploit it, we have a look at man mPlayer, and believe me, man mPlayer is pages long. But we do find 2 very interesting variables, dump file and dump stream. So dump stream tells mPlayer to save whatever stream it receives to the hard drive, and dump file tells it where to save it to. Fantastic. And bear in mind, all of this is running as root as well, so that's a whole nother issue. So we can actually now start to overwrite pretty much any file on the system. And that's all it takes to do it. So we give it this playlist file. We tell it to play this playlist file that has these 2 parameters in, dump stream, dump file. So dump stream set to true. Let's dump what we download. Dump it to here. And then we just download something that's whatever we want to run. So we can actually just download an arbitrary binary and put it anywhere on the file system. I say anywhere on the file system. We do have 1 or 2 limitations. As with all Linux, you can't overrun you can't overwrite a running process binary. So some of my ideas for doing it there went straight out the window. Root is mounted read-only, so there were only 3 root directories that were read-write. So Karotz, user, and var. So ideally, I need to overwrite something in one of those, excuse me, with a binary that will then get run next time, or that I can make get run. So several options. Do overwrite something in etc, because that was stored under one of those subdirectories. Okay, might require a reboot to start. Overwrite a shared library. Okay, yeah, can be done. Overwrite a Karotz-specific daemon. I'm lazy. I went with the last choice. It seemed easiest to me at the time. So putting it all together, right. So to bring this to an end-to-end code execution vulnerability, or sorry, exploit, we need to crash the controller service to reset the interactive ID parameter, use the authentication bypass to start mPlayer to load our malicious playlist, overwrite a module which is then loaded by the controller service when the controller service starts, and crash the controller service again. So it then runs our binary. Bit of a chain there, chaining a couple of the issues together, but hopefully it'll all work. I say hopefully it will work. Let's see if live demos will do it. What did I call it? I think. Let's see. Brilliant. Yep, so looks like in this case that has done it. So we crashed the service initially, reset the interactive ID to null, log in, tell it to play our malicious playlist. It downloads the shell, saves it. We then recrash the service, and it loads our shell. So hopefully, oops. I say, oops. Typing in front of lots of people. So there we go. That's kind of the culmination of far too many months of my life. But it wouldn't be right not to get that far. Oh, far too far back. Sorry, trying to find my place. So so the final tally, so ended up with 2 vulnerabilities and associated libraries and applications. Okay, so one of them was already known, but one previously unknown vulnerability in libmms. At least 3 vulnerabilities in the Karotz controller. There were probably 1 or 2 more there that I didn't investigate, but we did get our desired outcome. But to be honest, it wasn't really about the outcome. It was proving that the rabbit couldn't beat me. And my ego is that fragile. I mean, some of you may be very concerned about the research I'm presenting here. If you have one of these devices, I do have several, what can you do? So obviously you reported these issues to the vendor. However, the vendor has been particularly non-responsive. In response to one of my disclosures, they sent me an email saying, we apologize our servers have been unavailable. They will be fixed soon. It's not the question I asked. So they appear to be kind of concerned with availability at the moment. The devices appear to no longer be sold. Believe me, I tried to buy a third, and I couldn't. They'd sold out everywhere. I was on eBay for quite a while trying to get one. But the server's quite offline quite often. I'm starting to think this is abandonware. So if you do have one of these, please do firewall it. If you can, update mPlayer, libmms, all the rest of it. And implement your own server, because theirs go down all the time. But then, again, this wasn't about the end outcome. It was about the process. It was about learning a bit more. Before this, I'd not done much ARM reverse engineering. I was mostly x86. So it was another chance to get involved and get my hands dirty with this type of VR and RE kind of thing. Hacking toys can be fun. Hacking most things can be fun, but toys are actually a really good place to start. Security is often an afterthought. They obviously had considered it in some bizarre ways on this device, but not adequately. And just because somebody's looked at it before doesn't mean there aren't more vulnerabilities to find. So Dan Crowley of, let's say, Spider Labs, he'd looked at this. He'd done some research on this, and he'd got it to the point he needed it at, and that wasn't satisfactory for me. Took it one step further. If anyone wants to pick up the baton from me, please do. I'm sick to the back teeth of this thing. And I think that's about all I've got for you. So if there are any questions, please feel free to shout them out or come see me afterwards. If anyone wants to see its ears move again, then I can do that too. Thank you.